Welcome to Plants, People, Science, a podcast of the American Society for Horticulture Science, where we talk about all things horticulture. I'm Curt from the University of Arkansas, your co-host, along with our co-host, Samson Humphrey from North Carolina State University. Sam, how have you been?
I've been all right, Curt, but admittedly, I haven't gotten to see much natural light recently. I've been under electrical lights, writing on my laptop screen. I'm finishing up my master's right now, so honestly, I've mostly been inside just doing a lot of writing. How about you?
Well, I'm a little bit of the opposite. The semester's ended and I'm into my summer work. So there's a lot of field work and then my major hobby of gardening. So I'm out under bright sunlight a lot. And, plants are green, the flowers are blooming, days are really long. That always makes me think about light. Light and photosynthesis were something that I've spent a lot of my career studying. So I guess I enjoy being in the light. I don't photosynthesize, but I sure like sunlight.
If anyone could photosynthesize, Curt, I think it would be you.
Well, I hope that you're prospering under electrical light. I know that's the part of your career that you're in, and you'll soon be doing other things as well. And hopefully you get out into some natural sunlight. But light is so important to plants and so important to how we grow plants.
It is. And the research that I've done and that many other people do has shown that if you change the quality, the color, the intensity of light in electrical lighting, you can maybe mimic sunlight better, or maybe you can cause plants to respond differently. So that's a little bit of what we'll be talking about today.
Yeah, I get really excited about that. In my career, we started with high pressure sodium bulbs and a lot of conversation about that, and mercury vapor bulbs. But now with the introduction of LED lighting, and although LEDs have been around for quite a long time, the affordability of it, the ability to control light, that's a whole new kind of path and avenue of research and understanding how plants respond to light and how we can control that and modify plant growth and productivity.
Yeah, there's been a real boom in lighting research, and you really see that at ASHS conferences as well. Over the past couple decades, there have been many more researchers presenting their light research at these ASHS conferences and publishing in the ASHS journals.
Yeah, I'm excited. We had that symposium at the recent conference on far red light, so maybe we ought to just dig into this episode and hear what Dr. Runkle has to say.
Dr. Runkle, welcome to the podcast.
Thanks, Sam. Pleasure to be here.
Do you think you could start by briefly introducing yourself?
Yeah, my name's Erik Runkle. I'm a professor and extension specialist working in greenhouse and floriculture crops. I'm at Michigan State University and have been in the department over 20 years now. And I have a research and extension appointment. So most of my research is applied and hopefully serves to help the industry in some way, shape, or form in the short to medium term future.
Dr. Runkle, as a colleague, I've been watching your career, but for our audience, why don't you tell us a little bit about your area of study, your discipline? And you and I share the interest in light and plant response to light. So maybe can you tell us, how did you get interested in plants and light?
Great question, Curt. It was really my master's degree, my master's thesis research, where I was introduced to light, and I studied the effects of day length on flowering of a wide range of herbaceous perennials. And so I gained an appreciation for how light can regulate flowering, the flowering process in a wide variety of plants, and how it varies quite a bit from one crop to another. And then it was my PhD research that continued on the theme of light. But the focus there was looking at how different wave bands or colors of light influence not only growth and elongation, but also flowering responses. And so when we studied light, it was, back then we didn't have LEDs. They weren't common. They weren't viable for research. And so we looked at what happens when you remove certain colors of light from the sun. And that was pretty informative. It really sparked my curiosity and interest, not only in terms of light regulating flowering, but light regulating the growth of plants.
I find that interesting. I think about my career and probably yours. There's been so much development of the technology and the science. When I was a master's student, the crude ways we used to measure light, and the understanding of wavelengths, and we really didn't have good ways to control it. And now you have the breakthroughs of being able to use and measure PAR. So it's been kind of interesting. And I find light to be just a fascinating thing. I mean, I know that we use it to create energy. We use it for solar panels. But it's interesting that it also energizes and cues so many plant responses. Tell us a little bit more about this. The short day lengths we have in the winter and leaves have fallen off the tree. As a tree physiologist, I find that phenomena interesting. Tell us some of the responses, the general responses of plants to light, wavelengths, and duration, so that our audience might understand it better.
Okay, well, how many hours do you have, Curt?
Well, okay then. Just give us the abstract version. You can keep it brief, or maybe focus on the kind of things that you like to study. What about light is really exciting to you? Maybe that's the way to go.
So when I think of light as having three dimensions. First is the intensity of the light, which we can measure on an instantaneous basis, or more often we're interested in the cumulative amount of light. And that dimension is what primarily regulates the biomass or the growth aspect of a plant. So it affects shoot thickness, the number of branches, the rooting. It can affect things like fruit fresh weight, harvestable index. We think of that as a primary factor that affects just plant growth, shoot and root growth. The second dimension we think of is light quality, or the spectrum of light. And that's really been my focus, which has been to look at how blue light, green light, red light, far red light, UV light influence plant growth and flowering in some cases. And so it affects not only flowering, but the architecture of a plant, things like leaf size, stem elongation, the overall plant morphology. And then, of course, the third dimension is day length, or photoperiod, and the number of hours of light and darkness per day. And for a lot of crops, and especially ornamentals, that can regulate the flowering process. So we have short day plants that flower when the nights are long and the days are short. More commonly with ornamentals, we see they have a long day response, meaning they flower when the days are long and the nights are short.
But as a human, not as a plant, I always feel like I'm kind of limited because I can just see visible light. And that visible spectrum is pretty small. But what you're telling us is that plants perceive light maybe more than visible light that we can see. And again, in my area, I've always focused on photosynthetic light. So I was looking at, the traditionally and historically what we've called photosynthetic active radiation, approximately in the wavelengths of 400 to 700 nanometers. But tell us more about the outer bands, the ultraviolet, the far red, and the infrared wavelengths.
Sure. Yeah, so it's not surprising that we're biased to understanding light based upon our own experiences with it. And it turns out that the human eye is very biased towards light, and we see green light very well. It appears very bright to us. We have very good perception of green light, much less so as we get to shorter or longer wavelengths. So we do see blue. Obviously, we see red light. But if we consider the number of photons of blue and red, it appears much dimmer to us than if we had the same number of photons of green. And then right when we get into the UVA region, and so that would be on the shorter wavelength, around 400 nanometers or less, we get to a point where we can't see it anymore. And so that's on the high energy wavelength side of the spectrum. On the lower energy but higher wavelength side, we have far red light. And again, we can't perceive that by our eye, but plants are very responsive to both UV light and far red light. And so we have to be careful. And actually, until somewhat recently, there was a human bias in recording and measuring light because we were basing it upon the human eye and not on photons, which is really what plants respond to in terms of growth and in terms of morphology.
So today we're talking about the number of photons that are reaching plants and the colors of those photons and how they affect plants differently. We reached out to you because we're really excited to hear about far red radiation. So could you elaborate a bit on how far red affects plants?
Right. So we can define far red in different ways. Most commonly, it's defined as the wavelength from 700 to 800 nanometers, or I think increasingly some are suggesting we should shorten that so it's 700 to 750 nanometers. So again, it's not a wavelength we can see, but it's abundant from sunlight. Actually, there's a similar amount of far red coming from the sun as there is with red light as well as green and blue light. And so it has a pronounced effect on the shape of the plant. And some of the earliest work we did with LEDs actually was looking at far red light and how it and other colors of light control the flowering process of plants that are responsive to day length for flowering. So far red is known to elicit what we call shade avoidance responses. So these are responses that when a plant perceives shade, and usually can be from different ways, but one of the most common ones is when there's a relative abundance of far red light relative to other colors of light, and especially relative to the amount of red light. So when we have a relative abundance of far red light, the growth response of the plant it's a signal that the plant now needs to respond to capture sunlight that's available, or whatever light is available. And so it's a response, kind of a flight or fight response. And so it can't fly, so it's got to fight. And so what the plants will typically do is the leaves become larger, the petioles elongate, the leaf area increases, and if it has a stem, the stems elongate as well. And so it's really trying to expand itself to try to capture the photosynthetic light that is available.
So maybe a plant at the bottom of the canopy might be getting less of that red light, less of those other colors, and maybe a greater proportion of far red. And so it does this stretching effect to reach and get more light.
You said it just right, Sam. So leaves absorb most of the green, blue, and red light, but they transmit or reflect most of the far red light. And so that's why the ratio of far red to the other colors changes as it penetrates through a canopy.
Erik, and as I said previously, technology's really changed, both in our ability to measure light and light intensity, as well as the wavelengths of light. And now we actually, with LEDs, have better ability to control light for plants. I mean, we've gone from using a sledgehammer to tweezers on this. How is this technology, both in the ability to measure light and the ability to control light, opening up new areas of science, new aspects of horticulture for us? Are we becoming illuminated?
That we are, Curt. So really the advancements of LEDs in terms of their output that has been increasing and their cost that has been decreasing has really enabled a new frontier of research with lighting. Some of the early studies were done actually back in the 1980s with LEDs, but that was by a select few, specifically those involved with NASA, where they had a healthy budget to work with LEDs. And so that provided some very important foundational research where people were able to deliver very specific wavelengths and specific intensities to really understand the fundamentals of plant growth and how different colors of light influence plant growth. And then as the technology of LEDs has advanced, and it really picked up around 2010, we've seen the number of researchers getting into lighting has dramatically increased. And with that, our understanding of how the different colors of light, the intensity of light, and how those interact with each other to regulate different growth and development processes of plants. So it's given us a really powerful way to manipulate the light spectrum and intensity at the same time. And it's one of those things that the more you learn about light, the more questions you have. And so while there are a lot of people who are looking at lighting, looking at understanding light and effects on plants, there's still not a shortage of research areas to pursue.
And it's exciting too because so many of those research areas are so close to physics. I had my first introduction to horticulture through agronomy, and it's always been very plant focused. But then when I first started learning about lighting, it was so much more physics than I ever expected. So it's really wonderful to see these two fields very closely related through light. But it also brings up some really interesting questions of how physics professors understand light and how horticulturalists and plants understand light, and has brought questions about, like, for example, PAR and if we should extend PAR. Could you elaborate a little bit about that?
Yeah, so PAR is an acronym for photosynthetically active radiation. And it was the foundation of it was based on some pioneering research performed by Keith McCree, where he looked at the effects of different colors of light on relative photosynthesis. And it was very important research. It had its limitations, but of course, this was done before LEDs were available. And so looking at the growth response on an instantaneous basis, looking at, all the way from the UV range up to the far red range, we could see that arbitrarily you could select the wave band from 400 to 700 nanometers as the region that is what's most effective at increasing plant growth. Now, so because of that, the definition for PAR considers that all photons in that wave band from 400 to 700 nanometers are equally effective at increasing photosynthesis and thus plant growth. Now, there has been more research with far red, especially in the last 10 years as far red LEDs have become more common. And it has enhanced our understanding of how far red light not only affects morphological responses such as plant acclimation, but also how it affects photosynthesis. And there's well-known response called the Emerson enhancement effect that has shown that the simultaneous delivery of far red and red light is better than one or the other. And so we've known that far red is important for photosynthesis, but I think with this additional research with far red, there are some studies that show that far red photons, in some cases, are equally effective at stimulating photosynthesis as red photons or green or blue photons. And so there's some effort that we need to extend the definition of PAR to 750 nanometers. Some might even suggest 800 nanometers, but hence the term extended PAR or EPAR, where in that case, the far red photons would be considered equal to red, green, and far red photons.
As you've seen, sometimes science moves at a glacial pace because we have to have scientific fact and then prove a theory, and we have to have a preponderance of evidence. So it's really difficult to change paradigms like the paradigm of PAR being just 400 to 700 plus or minus nanometers. I guess now, has this new evidence, how are the scholars reviewing this? Is there skepticism about the new discoveries? Is it stimulating more work? Are people in general agreement? Tell us what kind of state of the science is. We don't have relatively new findings. Is there a preponderance of evidence starting to build? Does my question, do you understand what I'm asking?
Yeah, I do. And fortunately, those of us working in this area, it's a relatively small community, and it's a great community. There's a lot of mutual respect. Actually, that was one of the topics that we discussed at the last ASHS meeting, where we had a workshop focused on far red. And one of the main focal points was to discuss PAR and EPAR and what people's thoughts were between the two and advantages and disadvantages of each. And so the concept of EPAR really has been pioneered by Bruce Bugbee at Utah State University and Mark Van Ursel at University of Georgia, where they performed some pretty compelling research along with their graduate students and postdocs that showed very well that there was a promotion of photosynthesis with the addition of far red, and of course that supplements some of the earlier work. So as more people have studied this, I think there has been a growing consensus that we need to, at a minimum, report extended PAR or EPAR. I don't know if we necessarily need to not report PAR by itself, and I think in the best world, people are reporting PAR and EPAR, and for that, you might as well report specific percentages of other colors of light like blue, green, and red. So there's a movement towards PAR. There is also some caution, including by me, because let's take an extreme case where, okay, we know we can grow plants under only blue or only green or only red light. Their morphology may be pretty funky, but can we grow a plant under only high-intensity far red light? And, okay, maybe you could, but it's not going to be... Anyway, so it becomes a little bit subjective. So I think there may be some constraints with EPAR, but I think including it as a metric is very compelling in scientific research.
So in this workshop, I love thinking about this because I have been taught that, as Curt said, science moves at a glacial pace, and we publish papers and build upon each other's work and show evidence, and it's sort of a slow process, all things considered. But then at ASHS Conference 2022, you held a workshop where all these scientists who have been doing this work and have spent their whole careers looking at and trying to understand plants and light and the interactions, they all got together in a room to discuss. So I find that so valuable. Thank you for running that workshop. I'm wondering if you could just describe simply the outcome of that workshop discussion.
Yeah, so we had speakers where they gave basic overviews of the different effects of far red light in the growth and flowering process. So the focus was very clearly on far red light. And then we had a lot of time for, I would say, debate and discussion, although there wasn't a whole lot of debate, but people sharing their thoughts and experiences and research with far red and the merits of including far red in the spectrum, in the spectrum that we should be reporting in plant science. And there were people, it was a very well-attended workshop, a lot of academics, a lot of graduate students, and I was glad to see also quite a few from industry. And if you think about industry, they're creating these LED fixtures, and whether we consider far red in being light that is useful for plants can really drive the design of these different fixtures for various reasons. And so I was pleased to see that there were lighting companies in particular that were at this workshop. And so I think we walked away with a general consensus and agreement that far red light, as we know, has a big role in the growth cycle of plants, and that we should be reporting it. And there's still some questions about whether when you design treatments, you should have treatments that have equal number of photons in the PAR region, or do you include also far red light? So there's still different ways to do research. One is not necessarily right or wrong. It's more important that you clearly define your wave bands in your treatments and the basis for those treatments.
Again, I find that very interesting, Dr. Runkle. One of the things about horticulture that our sciences are both fundamental and translational. They're applicable. What do you see? I've got two questions, and you can answer them in any order you want. What is the frontier of this new light science? And what are the new questions that are emerging from our discoveries? That's one kind of thing I'd like you to address. The other is, so what? So what? We now know this, but how do we apply this? And where does this information fit? Is it useful, or is it just some sort of arcane knowledge?
Well, I certainly hope it's not arcane knowledge. So let me get to your first question, the frontiers of this research. And I don't have a real clear crystal ball on that. I think there are a lot of questions that we still have. And some of those questions are limited by LEDs and what peak wavelengths are available for far-red LEDs. And so there's really one major type of far-red LED. It has an emission peak that is around 730 nanometers. I think there's a need for more research where the peak wavelengths are beyond that, both lower or higher. I think we generally understand that once you get beyond 750 or 760 nanometers, that there's less or perhaps no utility of those photons with respect to growth or development of a plant. But I think we need to understand much better than just subjectively choosing 750 because it's a round number, to have a little more science behind where that cutoff is for the higher wavelength. So I think that's one thing that, again, is going to be limited by technology. However, I do think there are some other approaches that we can tackle that problem. Also, I think questions about far red and interactions with other colors of light. So far red and blue interactions are something that I'm studying and very interested in. Blue and far red light in some ways act antagonistically. So blue light typically suppresses growth and elongation. Far red light typically promotes elongation. And so then you have this interaction between the two, and which one wins, right? Which one can offset the other? And so complexities that exist with other colors, as well as far red interaction just with absolute number of photons, so light quantity, and whether or not the far red light effects diminish as light intensity increases or not. So those are just off the top of my head some of the areas I'm personally interested in, and I think there's still questions about. In terms of what does this all mean? Of course, it means more for us who are in plant science and lighting research than many others. But I think ultimately what we want is to create environments to grow plants where we are maximizing growth while considering inputs. And so if we're growing plants in a greenhouse or indoors, in cases where we are enriching the spectrum, for example, with supplemental lighting, the question of delivering far red light or not can have an economic impact on the crop. It can affect the quality attributes, potentially the harvestable yield, things that will matter to the people who are growing the plants and ultimately to the consumer. So we are understanding far red and the effects, and of course, not everything is good. I mean, there are some trade-offs that exist with far red, is that you may get bigger leaves, for example, but it could come at the consequence of changing the texture of a leaf if it's something you might eat, like a lettuce. It can decrease the coloration of a leaf, so a leaf may not be as dark green or as purple with far red. And so understanding all of these effects of far red light, knowing that there will be some trade-offs, and keeping in mind when we're growing horticultural crops, we want to make sure that we're not resulting in an inferior product when it's sold to consumers.
It makes sense why it started with NASA and their technology. Of course, we want to feed people in space stations. We want to go to Mars. You have a very compelling argument that this will have an impact on feeding 8 to 10 billion people in the next 30 years if we do more protected agriculture. So it is very fundamental, but also very applied. It really has significant impact because I do pay attention to what my lettuce is like. I have one more question. It's not necessarily in your area, but just was curious. When we think about plants absorbing light, the primary antenna for light absorption has been a specific kind of pigment. In the case of photosynthesis, it's chlorophyll for absorbing PAR. Have phytochemists identified pigment systems or other chemical systems that are perceiving or absorbing these other wavelengths of light? I just don't understand. Or is it chlorophyll?
Yeah. So there is, so far red, of course, can be useful in photosynthetic reactions, especially lower energy far red, so 700, 710 region. But then there's phytochrome, which are, the pigments in all plants, at least light-grown plants, that perceive the ratio of red and far red light. And there are several types of phytochromes, and it's been very extensively studied in Arabidopsis, looking at mutants of individual phytochromes and understanding what happens when these plants lack one or more of these phytochromes and how growth is different from a plant that has the full phytochrome components. One of the challenges that exists, though, is that a lot of this research is based on Arabidopsis, which is a weed, which is a plant with a very short crop cycle. Seed to flower is 4 weeks, for example. So knowing phytochrome responses in Arabidopsis, and of course other plants too, there's certainly some similarity, but there are also some differences that can exist from one crop to another. So I think as more work is done with far red and specifically with phytochrome mutants or transgenic plants that maybe overexpress phytochrome, we will continue to improve our understanding of the role of phytochrome in mediating these responses to far red as well as other colors of light, such as red light.
That's wonderful. Thank you, Erik. It's also interesting, too, because phytochrome also absorbs within blue wavelengths, right? And so there's so much research. I was excited to hear that you're interested in blue and far red in combination in your research. So there's so many things people could study, so many different crops, so many different wavelengths of light and combinations like you were talking about. It's really exciting to see this work evolve. If you were a student and you listened to this podcast and learned about how the colors of light affect plants, and if you wanted to learn more, where would you go?
I mean, the first impulse is go to the internet, right? And start typing in keywords that are of most interest to you. So that could include far red, if that's what's exciting, or blue colors, or light quality. Type in crops that might be of particular interest to you to see if maybe there's a combination of, keywords when a study has been performed on that, especially for horticultural crops. So that would be probably more for the plant science side. Go into Google Scholar and start typing in keywords and seeing what are the most recent papers that have been published the last 5 years, for example. So that's at least my go-to of how to find information, is just going to the internet and doing a search. There are also ways you could, learn about the people who are doing this research, and there are quite a few in the United States as well as many other countries, to learn what their active research programs are studying. There is, so that's the scientific side. If people are more interested on the application side, there are a lot of grower articles out there that I and many of my colleagues have written about light and plants, and specifically about far red for those who might be interested, or other colors of light. And so that can be information that's a little more digestible, right? Papers or articles that have been written for not a scientific audience, but maybe a more professional audience or an industry audience. So I guess that would be my approach. Actually, Sam, I'd be interested to see. I mean, you're interested in this area. What are ways that you try to find information and seek more information about light quality?
I'm a little bit biased, Dr. Runkle. I would go to ashs.org and find the journals tab, where ASHS has 3 journals where they publish publications relevant to this. And I would search that specifically because I know those papers are of high quality. And I know you've published in those journals as well. I would say sometimes you can find scientists who make amazing extension materials, like Dr. Bugbee, as you mentioned earlier in this interview. He has a website where he publishes some of his lectures that he's given to classes, and you can watch some of those online. Lectures and abstracts and things from previous ASHS conferences. So that's where I would go in addition to what you described.
Speaking about our journals, with this kind of new information and new considerations, are you visiting with editors and reviewers that instead of just saying, I measured PAR, they should start reporting the wavelengths that they measured, the technology that was used to measure that? I mean, I've got a bunch of PAR sensors that aren't going to measure what I might need to measure now.
That comes up when I'm reviewing papers that are focused on light quality. And so if they're studying that, then I think it's an absolute expectation that they have measured the light spectrum and are reporting it. And so they would include blue, green, red, and far red light. And even if they're not studying far red, it would be important to know the lamp type or some of the characteristics so that if we wanted to find that information ourselves, the information was available. So if we were to review a paper, whether it's for an ASHS journal or another, that's the opportunity we have to provide feedback. And if we feel very strongly about something, we can write a short justification for maybe a fundamental flaw that's sent to the editor so that they know that this is a pretty important aspect that has either not been reported or perhaps even overlooked. In terms of how we try to move this forward with EPAR, I think we go to a lot of the same meetings, ASHS meetings. We see a lot of our colleagues and talk about these things in their papers and presentations focused on PAR, and there we can emphasize the importance of reporting PAR and EPAR when it's relevant. As well as in papers, we can talk about PAR and EPAR in the same breath. And when we have opportunities to talk about PAR, whether it's with colleagues in academia, graduate students, or industry, we can talk about far red, some of the advantages and disadvantages and when it comes to reporting, when it may not matter.
Well, this has been very enlightening, if I can say that with a straight face. It's been informative and fun. Like I've said, I became a horticulture physiologist because I heard an interesting lecture on light in an undergraduate physiology class. And so is this, the kind of additional step for me understanding and learning about the impact of light. And I can see it. It's opened my eyes for real. I understand light a little bit better. Sam, what do you think?
I really love this conversation. I love talking about light in general, so it's not a surprise. But hearing from one of the scientists that's at the forefront and who is helping drive this conversation, promoting good science and trying to move the needle forward with our understanding of how plants respond to light. It's just wonderful to talk with you, Dr. Runkle.
The ASHS podcast, Plants, People, and Science, is made possible by member dues and volunteerism. Please go to ashs.org to learn more. If you're not already a member of the ASHS, we invite you to join. ASHS is a not-for-profit, and your donations are tax-deductible.
This episode was hosted by Samson, Humphrey, and Curt. Special thanks to our audio engineer, Andrew Sheldorf, our research specialists, Lena Wilson and Andrew Sheldorf, our ASHS support team, Sarah Powell and Sally Murphy, and our musician, John Clark. Thanks for listening.